CFD stands for computational fluid dynamics. So the name itself is talking about fluid dynamics. It does not mean that we can deal with only the fluids, because wherever the gradient is available, the gradient in the form of either pressure drop or pressure difference, or you have a temperature difference, or you have a species transport difference, or you have a uh, like you can say in the form of uh, transport properties so whenever we have a gradient is exists, so the deal of transport phenomena is talks about basically the fluid dynamics. So fluid dynamics in the sense is not only related to fluid dynamics, so it can deal any type of behavior where the transport phenomena is existed. So the fluid dynamics is started in the 19th century by Louis Richardson to predict the weather forecasting. So nowadays CFD is become the very powerful tool. Uh, so to study the flow behavior, temperature gradient, concentration gradients, and all the stuff. So here I given one of the example of duct. As a simple duct, you can see in regular basis anywhere. Either you can see in house or any is the simplest practical application where we can apply the CFD. So here we have a duct. The duct have one inlet at the bottom side, and it have four outlets. So the amount of the fluid which is coming from the inlet, it will be distributed across the four outlets. So usually any person eager to know what is the percentage of the fluid is coming out of each outlet. So this type of real case scenario we can see in outside when the tank is at the top of your house and we have so many pipelines and we see the flow coming from the tank to the house. Uh, so this type of phenomena you can visualize with this small type of duct. So here the CFD is applied to duct. How we can emphasize? We study the fluid behavior, how the fluid is passing inside the duct, and we can study the fluid recirculations. Is there any reversal flow? And if have any heat transfer applications, like if fluid is entering with certain temperature, how the heat transfer phenomena is happening. Let assume in this duct, same duct, we have a different types of chemical species entering. So we can see the concentration of the species at the each outlet. So to understand this, for any simpler duct, for a fluid motion or species motion or heat transfer motion, we need to understand certain engineering basics. So the engineering basics is applicable to fluid dynamics. The fluid dynamics is talks about so the fluid mechanics with the dynamic combinations. And if you want to know the how mathematically we can relate this fluid behavior, so we need some mathematical functions like numerical methods. And also if the fluid is having like heat transfer phenomena, so we need to understand the heat transfer subject. And if the chemical reactions involved in this flow, so we need to understand the chemical reaction related stuff. So based on that, we need to understand the corresponding subject, and we need to understand the outcome of the flow behavior, or you can study the heat transfer behavior, or you can study the species transport behavior inside a simpler duct. So firstly, I am going to explain what are the fundamentals available in fluid mechanics. The fundamentals available in fluid mechanics is, first we can start with the basic equation that's called continuity equation. The continuity equation is talks about the mass entering into any system is equal to the mass leaving the system. Here the mass in the sense the mass flow rate. So the amount of the mass flow rate entering into the system is equal to the mass flow rate leaving the system. So this is the basic continuity equation. And apart from this basic continuity equation, we need to go with the dynamics part of the fluid, that is called Navier-Stokes equation. So the Navier-Stokes equation is just similar to what you read in engineering, that is called Bernoulli's equation. So, but only the difference between the Bernoulli's equation and the Navier-Stokes equation is the viscosity of the fluid is taken care by the Navier-Stokes equation. In case of Bernoulli's equation, the viscosity is not considered. So the fluid assumed to be inviscid fluid for a practical application. So that's why in the textbooks we can read what is the example for the fluid dynamics part. But in real scenario, each fluid have some viscosity. So we need to consider the viscosity characteristics of a fluid. So we need to consider the viscosity behavior of the fluid in practical scenario. So we can modify the Bernoulli's equation by incorporating the viscosity terms, that is called Navier-Stokes equations. This Navier-Stokes equation along with your basic continuity equation leads to a basic equation for the CFD. So this basic equation CFD is inbuilt in a lot of industrial application solvers. Next, if we come to the part of heat transfer, the basic equation for the heat transfer is like the conduction equation and the convection equation. And if the radiation is involved, we need to add the radiation equation. So if the fluid with heat transfer characteristics, we need to solve the continuity equation along with your Navier-Stokes equation and the presence of the heat transfer equation. It may be a conduction equation, it may be a convection equation, it may be radiation equation. So let's assume you have a chemical species. We need to add one more equation in the form of transport of chemical species. So if we see in the overall, your equations are increasing as the nature of the problem is increases. So mathematically solving or theoretically solving this type of behavior is very, very complex. So nowadays, lot of industrial industrial software is available in terms of the commercial purpose. So most of the people are using commercial software to predict and understand the behavior of different geometrical shapes by using these concepts of fluid dynamics. So if we come to the fluid dynamics part or CFD part, it have major two scenarios. So if we come to the virtual, I mean simulation part, it has meshing part and it has solving part. The meshing part is talks about the domain division. So we have a complete geometry. Let us assume the geometry is a duct. This duct will be converted into the mesh. So that called division of the geometry in terms of the mesh. Next is solving. The solving where the physics of the fluid dynamics will come into picture. So the continuity equation, Navier-Stokes equation, heat transfer, etc. and etc. will be the part of solving. So before going to solving, we need to prepare the model for the solving. So the model in the sense is the division of the geometry into a desired shape. So this is like a virtual simulation. Apart from virtual simulation, we have two more cases. So if it is a small geometry, we can build the prototype and I can do the testing. If it is a very complex shape of the objects, very difficult to go for prototype and testing. So this is always not a correct method. So we can go for in terms of the cost point of view and the time saving point of view. So people will believe like the virtual simulations are better optimistic and we can go with and produce the results and study the behavior. So this is like the introduction and overview of CFD. This is the application slide of fluid dynamics. So very traditional application is aerospace. So people use it to using CFD very more and predominantly in aerospace industry. This is the first, the aerospace industry. Here, some one of the example I given here to study the uh, aerodynamics over the aerofoil. So the wings of the aeroplane is like designed like a aerofoil, so that the smooth flow around the wings will have a better advantage in terms of the CD. CD means drag. So when the aircraft is moving with higher speeds like 800 kmph or 900 kmph, so it will tend to separate or it tend to resistance against the fluid motion. So the profile of the aerofoil shape is very very important for aerospace application. This is the one area where people most of the people use CFD. And similarly, one more part is when the aircraft is landing, so the landing gates will be come out of the interior body of the aircraft, and we can study the flow separation when the aircraft is landing. So this type of some of the examples where we can apply the CFD. And similarly, you have a the cabin inside the aircraft. We have a HVAC where the airflow passing through each duct, and it is keeping the passenger at comfort condition even at higher altitudes. So this is the one of the traditional approach. And if we come to the second approach or application is the automotive. The similar applications, so how we can apply to the aerospace, we can apply for automotive also. So we can use to predict the drag of the vehicle when the this is the example of passenger car. The passenger car is moving with high speeds like 120 kmph or 100 kmph roughly. So how the resistance offered by the air against the high speeds. So you can study the flow separations. You can see these image, how the flow is separating when the vehicle is moving with high speeds. These separations are very, very important to design the styling of the body. So always we'll try to make smooth line flow, try to avoid these separations. This is the one application of automotive. Similarly, we can carry out the HVAC analysis for the automotive, where the passengers will try to keep comfort condition when the AC is switch on. So I will show the case study of HVAC in the coming slides, how we can do that. Similarly, nowadays the electronics industry becomes very very important. So CFD we can apply to electronic industry. This is a one type of PCB. The PCB is talks about printed circuit board. So the printed circuit board it having a lot of modules. Each module having some heat capacity. So we can study the temperature of study the temperature prediction of each module and how the flow is happening inside the cooling pack. So this is the one of the application of electronic industry. Similarly, you can go to the chemical. This is like vortex generator or like a rotating box. How the fluid is mixing inside the vessel. So how the turbulence is generated inside the vessel because of uh, motion of the vessel. For practical example, you can simulate the chemical in terms of the washing machine. We have a washing dish where it is rotating with certain RPM. So how the fluid is induced, how the vortices are induced due to motion. This type of behavior we can predict by CFD. This is one of the application. And very very important is nowadays the CFD comes into picture on healthcare. So this is like lung structure where we can model the lungs and we can study the air motion inside the lungs. So we can study the where the dull cells is available by seeing the zero air motion. Similarly, we can apply the CFD applications to the sports. This is like the football, and NASA is predicted the CD of the football recently played last World Cup. So we can apply the flow separations over the football in sports, or you can apply the when the cyclist is pedaling the cycle with high speeds, how the flow is separating from the cyclist is also one part of application we can see. And this is like flying saucer where we can see the uh, flow motion around the flying saucer. And this is like turbo machinery where we have a turbines, rotations and power generation applications. We can see we can apply the CFD here also. So now I'm moving to the current trend. The current trend is very, very important in the industrial aspects. So the time is the most important. So any customer or any OEM people ask to the person, try to give as much as early possible if you get any work. This is the first point. And how much amount of the cost you can reduce. This is the second point. So for that, nowadays most of the industries are moving towards the automation. So all regular activities or repetitive works, the people are planning to automate it so the time and cost will be reduced. This is like workflow automation. And sometimes we need to do with the fluid behavior with respect to the structural. When the let assume whenever the fluid is hitting with higher velocities on a structural body, the structural body may be try to deforms or try to failures. So that type of scenario, we need to do the CFD with integration with some other solvers of structural. So we need to develop the integration part between the CFD and the structural in FSA problems. And this is like optimization. Optimization talks about we received one geometry. Let's say we received this geometry. We identify the what is the CD of this, and CD will be, let's say we got 0.5, or here we got here 0.37. Let us assume. So people talks about the air resistance is very high. So we want to reduce the air resistance. Let's say like 0.37 to 0.3. So if reduce the air resistance, my fuel efficiency will improve as. So, so try to change the shapes and try to reduce the flow separations and try to change the styling of the vehicle. So try to reduce the CD value to 0.3. This type of activity is called optimization. So this optimization is very, very crucial to develop and deploy a product in the for real-time use. This already I discussed about time and cost. And GPU. Now hardware is also very important to solve this type of applications. So nowadays GPU, graphical process units are coming into picture to solve this type of problems, to see the better visualizations of fluid flows. Now very, very interesting is like artificial intelligence. Some of the CFD companies are started by using artificial intelligence. So this is the example of artificial intelligence. So this is the same segment of the vehicle, like sedan type or assume. So they might be launched several sedans in previous history. They might be having the CD value of all sedan data. So now they want to launch new vehicle in the same segment. So they try to implement the artificial intelligence and machine learning algorithms, try to build the algorithm and try to test that, and try to try to predict the existing models. So if they are able to get the accuracy of the existing models with like 90 to 95% is, that artificial intelligence or machine learning algorithm will be considered as the best one. With that help, they apply for the new set of the data which are going to launch. With this, within a very short time or without any simulation, we can predict the rough value of CD, how much you are going to get in the same platform for a same vehicle. So this is the artificial intelligence application. Some of the companies are started already this. Only thing is we need the data for the same segment of the vehicle from the past history. Now, one more interesting is like now CFD have some open sources, so we can available free softwares, and outside we can use it as a free. That is called open source software. One of the example is like OpenForm. So OpenForm is a free library software. It's just like Python. You can use it, and you can solve any type of problems. So these are the some of the commercial solvers. One is like ANSYS Fluent. For Siemens is Starcesium Plus. For a Dassault system is the Power Flow. Mentor Graphics is Flowmatics. These are all commercial solvers we need to purchase, and the license cost will be around like minimum it starts with 30 lakhs to it will go to 1C also per year. And this is the what I talk about the open form. It is a free available software. Anybody is ready to download and try to use it. And these ANSYS, SimCenter, Dassault System, Mentor Graphics are all CPU based softwares. So this is called FVM solvers. That is called finite volume methods. So these will come in once the course session will start and all the stuff. And some of the solvers are used with graphical processing units, where they can use the Lagrange lattice Boltzmann methods. So the only difference this is we can see the particle tracing in the LBM methods. In the FEM methods, particle tracing is not directly we will see it. So LBM method by default is a unstudied solvers. FEM methods is a study as well as unstudied solvers. So this is the some of the technical content I am going to see for a application of automotive. So how the CFD applies to automotive. So in any automotive sector, you have a major branches where the people will work for different segments like external aerodynamics. This group will works for the styling of the vehicle and try to reduce the aerodynamic resistance when the vehicle is moving with high speeds, and thereby try to improve the fuel efficiency. This is the one group where we can work on external aerodynamics. This is the second part, second group, front grid analysis. So the front grid is talks about the bumper openings. We have a vehicle with a bumper. It has some openings where the air will pass through the bumper and it will pass through the cooling packs. It have a, some radiator condenser inside the vehicle. So here the objective of the our people are working towards the try to improve the mass flow rate towards the radiator condenser for a given opening area. And if we come to underwood thermal mapping, here we can see the temperature analysis where hotspots is more important, how to reduce the hotspots, and how much air is carried by the air, heat carried by the air when it's passing through all heated zones. This is the one group where people will work. Similarly, we have a very challenging task like multi-phase flows. Multi-phase flows, we have a like two fluids. One is air and other one is water. When the vehicle is moving in a pool of water, how the water along with the air having the resistance against the vehicle motion. Even the vehicle is moving very slow speeds, but water levels are accelerating at the bottom of the vehicle and is try to increase the water level. Maybe sometimes it may enter into the cowl pin, or it may be enter into the engine inlet or air intake. It may cause the damage, or sometimes the water may be enter into the electrical appliances where damage of electrical parts will be chances are there. So the group will talks about or study about the behavior of water when the vehicle is moving in a pool of water. So some of the typical job levels in the industry. So you can expect the people with lesser experience, like 2 to 3 years experience. So the first task they will give in the industry is like model preparation. So we need this is the like geometry. Let us assume duct. The duct will be considered as a circular. This is called pipe. When the fluid is passing here and leaving here, so it have some thickness. you can see the thickness in 3D image. So whenever the fluid is passing from here to here, it will touch only the inner surface of the pipe. So the main task of the engineer who is having less than 2 to 3 years experience, they try to prepare the model uh, that is called fluid domain, where the fluid is touching in the pipe here. So he will extract the inner surfaces and try to show here the final model after extraction. So this type of work activity should be considered for the lower level experience of the people, where he will prepare most of the time into the model preparations and the meshing tasks. If the experience is goes middle level, like 5 to 10 years, so then you will start slowly the analyzing the problem. So once your model is ready, you start analyze the problem. You start analyze the fluid behavior, if the temperatures involved, how the temperature, hotspots influence, and all the stuff is going to study in a level of senior. And if we are top level management, let assume it is a more than 10 years experience, the guy will take care of some team members. He will act as a group lead. So under him, some people, some 4 to 5 people are working at different segments. So his role is mostly onto the customer interactions and try to extract the more work and try to give the better resources for a given task and deploy the resources and try to give the best output for a given task from the customer. So these are the some typical roles in a CMD ladder. So this is the practical example where I told HVAC for a, this is like automotive application. The HVAC problem. This HVAC talks about heating, ventilation, air conditioning. So I have a HVAC unit. It has some inlet. It has some 4 outlets, 1, 2, 3, 4, and you have a some blower. This view is given here in the transparent. We can see here. It has some inlet, 1 outlet, second outlet, third outlet, 4 outlet, and you have a blower, and you have a some rectangular boxes. So this HVAC unit talks about heating, ventilation, air conditioning. So the heating is talks about heating of the fluid. So this red box is talks about heating of the fluid, that is called heater. So ventilating means we are giving the purification of the ambient air. So this part, before this part or this segment, you have some purification, so where the dust particle will be removed. And air conditioning is talks about we are cooling down the air to produce the cooling effect for the passengers inside the car. So the blower here, it tries to rotate with certain RPM, and it will try to suck the ambient fluid from this inlet, and it will pass through this and it will pass here. This is called evaporator. The purpose of the evaporator is to cool down the air which is coming from the ambient to lower temperatures. So this, after that, it will pass to the heater and it will enter into the different outlets. These outlets are connected to the IP, instrumental panel of your vehicle. So this and this and this and this. So these 2 rows or 2 outlets will be connected to the passengers straight away in front, and these and these will be connected to the outlets nearer to the window, side windows or side glass. So this is the geometry we received, and we'll try to prepare the model where the less experienced guys will try to prepare. So if you see the blower geometry will be like this. So all less experienced guys will try to do this type of activity. So take this model and prepare this meshing, and if you zoom this meshing, it will be look like, and the fluid volume inside the geometry is like this is the fluid volume, and this is the boundary layers. So in engineering we can study the boundary layers. The purpose of the boundary layers is to uh, to capture the fluid behavior with respect to the walls. Whenever the fluid is passing on a stationary object, we have a no slip boundary condition. Because of the no slip boundary condition, we have a boundary layer. So the boundary layer will be start growing from the no slip boundary condition, and within the boundary layer we have a very changes in the velocity gradients, temperature gradients, etc. and etc. To capture that gradients, we need some layers very fine to capture the gradients, that is called boundary layer. This will be called boundary layer. And if you see the fluid layer across this cut section, we have some of the boundary layers on the blades and some of the fluid particles inside the cut plane. And we have a evaporator and heater. These are the inputs usually we'll get from the customer. We have a coefficient like inertial coefficient and viscous coefficient. This inertial coefficient is talks about the pressure. The viscous coefficient is talks about the resistance because of the viscosity of the fluid. So we can model this evaporator and heater simple like a rectangular box, and we can give these as a input to the evaporator and heater in the solver. So that means we are not solving the complicated structure of the evaporator and heater. If you see the evaporator and heater, it has some internal pipes. So it has like small pipes inside the rectangular box. So we will not model the rectangular box. We will not model the small pipes. So we are modeling in a rectangular box, and the pipes resistances will be given in terms of the inertial and viscous here. And you have a blower. The blower will be is a rotating part where we can apply the multiple reference frame, that is called MRF approach. So in MRF approach, we can give as a RPM as an input. And we need some mass flow rate. When the blower is running at this speed, how much mass flow rate it will suck? So let's say 0.167 kgs per second of fluid is suck. So I need to give input here, so as a mass flow rate. And these outlets are exposed to the ambient condition. So my ambient condition is 1 bar. So 1 bar will be referred to 0 as a reference pressure. And to calculate the density of the fluid, we need the pressure and temperature conditions. From this, I can calculate the density. I can give as a property of the fluid. So if you see this physics of this problem, how you solve this type of problem, we have a constant density. The density will be calculated from pressure and temperature, and the exhaust wall distance is talks about the boundary layer, and this is the gas. In gas, it is air. We have a density and viscosity as input key parameter. And gradient is talks about flow gradients, and we have a turbulence. When the Reynolds number is goes on increasing more than 2300 in a pipe flows, it will call turbulent flow. So once the turbulence is entered, we need to solve the turbulence. So these are the turbulence equations, and this talks about study problem. Study means the flow behavior is invariant with respect to time, and this is like number of dimensions. This is 3-dimensional problem. We are going to solve 3-dimensional. This is like boundary layer capturing. So this is the physics how we set up in solver. Once the physics is set up, we can study the monitors and what is the pressure. This is the pressure variation. This is the velocity variation across the flow. Now you can see we have a dead zone. This is called blue is like 0 Pascal, and we don't have any the pressure. I mean, you can say this zone is no use because of sharp. So if you see the velocity, you can see here, because of sharp, the velocity is separating here. So we have a recirculation zone. So because of the recirculation zone, we have a dead zone here. This type of some inferences we can take and try to change the shape. That is called optimization. And this is like flow inside the HVAC unit, and what is the velocity at the outlets, and we can calculate this is the input, and this is the flow distribution from each outlet, and this is like pressure drop. What is the my pressure drop? And this is the target heat 800 Pascal. So my pressure drop is like 450 is excess, so I need to reduce this 450 excess. How we can go with, like, that is called optimization problem. So how to get into domain? So we need to have motivation, and we need to have more interest on mathematics, solving techniques, some coding like fluid dynamics, heat transfer, and also some innovative thinking. So, but mostly preferable is like ME, MS, MTech. BTech people also welcome, but most preferable is ME, MS, MTech. So this is the flow behavior and flow passage inside the HVAC unit.